And welcome back to Book Club. Finishing up the applied numerical methods. Again, doesn't be Python. MATLAB's a great tool. Not many people these days are programming straight into C++. But the idea here is that this book really kind of covers the basic tools that you're using as an engineer, as a scientist, in solving problems on a computer. And honestly, we all do it. I don't care if you're if what you do is like hardcore numerical methods, kind of like I used to do as a professor, or if you're building real things like I'm at Venus right now building rotating detonation engines. You still end up using numerical methods, whether it's just in Excel do calculations, or I use Python almost regularly now to do some estimations to help build real things. So this is a tool that you'll use across your career as an engineer and scientist. And so I'm kind of wrapping up here the last portion out of this book, which is boundary value problems. Okay, BVP first word, boundary value problems, and this is just differential equations, usually in multiple dimensions. It could be time, one dimension of time and one space. It could be multiple in space. But it's a boundary value problem where the last time we were talking about a function where we knew its derivative and we wanted to march it forward in a direction. Usually that's time. Usually our physics-based or chemistry-based or biology-based equations are on time. But I'm going to draw you an example here of one that we usually think about as a very basic boundary value problem, which is I have a rod connected between two balls, okay? And I have a certain temperature that this side of the rod is held at. It could be a water bath, it could be just a hot rock, whatever it is, and then on this side I have some other temperature. And there's usually in the heat transfer world we call T infinity, which is the ambient temperature. And so this is a rod. It'll have some thermal conductivity K. So thermal conductivity K, and the air could be blowing at a velocity. There's a kind of convection relation. And so this equation, when we write down some basic assumptions, what we would get along this equation is this, which is the the second derivative of function with respect to x plus h times t infinity minus t is equal to q. Now, if you've actually taken heat transfer, you'll probably see there's some dimension stuff. I'm just simplifying it down to you have something that's a function of the second derivative, something that's a function of the change, the actual variable temperature of this rod compared to, and then a heat source. So without getting into the physics or units of any of that stuff. Okay? This equation we can discretize, so we know how to do this with finite differences. And there's one way where you can take a look at this, and it's called the shooting method, where you can think of sort of x versus temperature starting at TA. And what you could do is you could take a different guess of the slope and see which one of these slopes will land you at temperature B. It's called the shooting method. It's not usually used, but it's a very basic idea, which is what you don't know is you don't know the full function across here, but what you really definitely don't know is the derivative. And so if you guess the derivative, you could actually solve for sort of the next step and kind of march your way along. That turns this boundary value of the problem into an ordinary differential equation. You can use all the tools we talked about last time, Runge-Kutta, things like that. Okay? Or you can go ahead and take this into the finite difference, right, where this would then look like t at I plus 1 plus t at I minus 1 minus 2t at I over delta x plus h t at I is equal to q minus h t infinity. Kind of putting the t infinity to the other side here. And that's a minus. Okay. And so the subscripts here, I, effectively meaning, the I kind of dividing this up into a whole bunch of different slices, and I just being a generic, location in there. And this, you could actually take a look and see if I stack all the unknowns on this vector Ti, that's actually a vector, and this whole thing becomes a matrix problem, where the right-hand side is this. Okay? And in 1D, you're going to see that this basically becomes the diagonal terms, which is the Ti. I have some off-diagonal terms, and then everything else is 0. So this is actually a very, it's called a tridiagonal matrix. It's actually very easy to invert. We talked about this. I think we talked about this in the matrix inversion section. And so you could do this, and you could use this to invert it, and you would have your solution. Okay, so that's why we spent so much time in computational linear algebra, because you can basically use these tools to boil this down into this form, which is, you know, ax equals b. Okay. If this is, say, a function of 2 dimensions, so this example is sort of 1 dimension. If this happened to be a function of 2 dimensions, which is solve this as a function of time. So maybe there's an initial temperature distribution, and you're trying to see, you know, does it warm up or does it cool down? Is this air cooling down? You now have sort of 2 dimensions, and so the idea here is if you actually, you know, do the formulas on this, what you can think of, this as sort of these boxes here being sort of the 1-dimensional problem, and so maybe you get that kind of tridiagonal system in there, but then you have sort of the other derivative, like the y derivative. If this is the x derivative, maybe the y derivatives will show up in this banded structure, okay? And so this would represent a partial differential equation. A very famous one is Laplace, where it's the second derivative, you know, so maybe this is the second derivative of temperature, again, back to a heat problem, is equal to some source, okay? Again, you could use this, finite difference formula. There is advanced ways, we usually don't use as finite difference. There's an advanced way called finite element analysis. And so, you know, I'm not going to cover it in this one. So actually, let me know in the comments. I've got a couple good FEA books that I've used, some good teaching ones, some advanced ones. So let me know in the comments if you want me to come back and do, I got to do either, you know, one additional video on the series about FEA, or I can really dig in an entire book. So let me know if that's of interest. It's definitely some of the background I had as a professor doing some of that stuff. I don't do a ton of it anymore in my role at Venus here as CTO, but certainly happy to do it if there's interest. So let me know. Okay, but FAA is sort of taking a domain. It could be very complicated. It could be flow over a cylinder. It could be heat transfer in a system. It could be vibrations of a drum. So FAA is how you would discretize these equations in a very complex geometry using, you know, triangles, squares, and solve that. It's actually a pretty powerful method, but it takes more than, it'll take more than just sort of one of these kind of little whiteboard sessions I'm doing here to get into it. So let me know, all right? But what you'll see with whether it's FAA or even here if it's just a finite difference, the rest of these entries here, I've kind of drawn with some markers. The rest of these entries are 0. So this is forms this A matrix, right? We're actually solving A, x equals b, where x is that unknown vector. This is pretty sparse, okay? And so there are a whole lot of solutions on how to handle sparse matrix. There's a whole like data systems analysis of how to do this. There's rearranging you would do if you go back to when we were talking about inverting matrix and how you can rearrange. There's lots of like reordering you might do to be able to speed things up. There's all of those iteration methods like precondition conjugate gradient. So all of this kind of comes back into, you know, why we covered those methods. The converting of equations to that is sort of, you know, where this sort of chapter was. And so, you know, there's a lot there that goes into FAA. Any of this discretization, again, you get into both meshing, okay, which is dividing that domain, discretizing that domain into whether it's triangles or squares in order to solve your differential equation. And there's a whole lot of computational geometry, okay, that goes into this. If you've ever used CAD, computer-aided design, right, all of that is computational geometries. It's like cylinders and squares and holes and cuts and unions and merges. So there's this whole realm here of computational geometry that is very related to FAA and how you actually model those surfaces, whether it's a part you're trying to do a stress analysis on a part, or trying to do a thermal analysis on a part, or trying to solve for fluid flow in a very complicated situation. Again, I've had some students go off and get into the NASCAR world, and it's, you know, very, very complicated flows, stresses, vibrations, you name it. And then certainly here, sort of in the high-speed vehicle, whether it's rockets or aircraft industry, all of this stuff comes into play on a very daily basis. So there's lots of tools, lots of good packages out there, and some free ones as well. If you're, you know, an academic university, don't feel like you have to shy away from some of these advanced tools. Either you can get a good discount with some of the professional tools, or there are, through kind of open licenses, MIT licenses, open source licenses, you can get some pretty powerful FEA libraries download and solve them. Okay, so it's really good stuff. And then I think the last thing I'm going to just share here is I talked a little bit about it last time, kind of this matrix. But if you have nonlinear terms, so in fluid mechanics, that's my forte. Okay, so you know, and I did a whole series really on fluid mechanics in the textbook. You end up having some nonlinear terms, and so they can show up in two ways. So either using the same notation. So if we have A times X equals B, but this is the unknowns, you could either have a situation where A is really dependent on X. So you kind of use that as a matrix here. Okay, is equal to B. That's one way that your nonlinear term can show up. This happens a lot in stress-strain problems, where depending on your strain is where your stresses show up. So this is one way that things can get nonlinear. The other way that can happen is maybe this is A is linear, but your right-hand side actually changes a lot as a function of X. Okay? And so fluid mechanics, this is usually where it happens in fluid mechanics. And then we have this other weird problem where in fluid mechanics, X is actually, I'll write as U, V, W, X velocity, Y velocity, Z velocity, and pressure, even in just an incompressible form. And we actually, in incompressible, the pressure actually acts as a conservation of mass. So you actually get weird numerics that can happen there. So there's an entire, that's why there are entire books and entire courses on computational fluid dynamics. So also, that's CFD. Also, if that's of interest, let me know. That's when I absolutely, again, back to my professor's days, I know pretty well, happy to go dig into a very detailed version of CFD and all of this stuff. Like there's really, again, there's some weird things that happen with pressure in incompressible. And then if it's compressible, you actually add energy and pressure. Pressure becomes almost a very different interaction when it's compressible, and pressure waves and things like that. So lots of things can show up. So, but these are kind of your two main nonlinear systems. And when you're, especially if this is a function of time, which a lot of time that's what's happening with either fluid mechanics, or you're trying to find a steady state. And so while it is a function of time, you're actually searching for the steady version. There's a whole bunch of stability criterion that come forth in it. So again, this is just scratching the surface. So again, if any of this is of interest, let me know in the comments below, whether it's FAA I can dig into, whether it's CFD. I'll probably come back on the next book club and do some kind of more engineering and sciences, but happy to dive in as there's interest. And so that's management value problems. That's really where this book ends. Is that you can think of it as it's what we did last time with an ordinary differential equation, where you need to find the right slope that either hits the right solution. So shooting method, but that's usually not the way that we do it. Usually we actually use our discretization, our finite differences, or FEA, to form a matrix that we then invert to then solve this boundary value problem. Again, where all this is an unknown vector of t, but you can either think of one unknown, these 2 points on t being known, or you can take this as unknown and know that those endpoints get rolled into this forcing function b. All right, that's it. That's for numerical methods. Again, the computer is your friend. One of the most powerful tools in engineering science. I don't care if you're not a computational person, you're going to use a computer. And so it's very valuable that you have at least this very fundamental understanding of what happens on a computer when you're solving these things, based on both the digitization and the discretization of whatever engineering, physics, chemistry, biology, science problem you're solving. Okay, next time.